All right, here's a much faster way to separate variables, and in particular, let's solve the following differential equation. Now, the trick is, you see this dy over dt, well, let's treat those as separate entities. And in particular, let's cross-multiply the equation. So cross-multiply, meaning here, multiply everything by dt to get t squared dy equals 1 minus t squared times y squared plus 1 dt. And now the idea is, just like before, let's put all the y's on one side and all the t's on the other side. So here we can keep the dy, but divide by y squared plus 1. And put the t squared on the other side to get 1 minus t squared over t squared dt. And then as before, since all the y's on the left side and all the t's are on the right side, we can integrate. So integral of dy over y squared plus 1 equals integral of, well, 1 minus t squared over t squared, but to make it a bit more presentable, let's split it up. So 1 over t squared minus 1 dt. And yes, this integral of 1 over y squared plus 1, it's this pesky integral, which is arctangent of y. So please, not ln of y squared plus 1. That's not correct here. And then here, remember 1 minus t squared. So 1 over t squared, that's t to the minus 2. And the antiderivative becomes t to the minus 1 over 1, or over minus 1. So we get minus 1 over t, minus t, and then plus a constant. And in particular, to undo this arctangent, you apply tangent to both sides. And then you get y is tangent of 1 minus 1 over t minus t plus c. Now, that is the general solution. And then to solve for c, and what we want to do, well, we want to use the initial condition, which is y of 1 equals 0. So careful, not y of 0 equals something, but y of 1 equals 0. So t equals 1 and y equals 0. We can plug that in to get a tangent of minus 1 over 1. So minus 1 plus c equals y, which is 0. So tangent of minus 2 plus c equals 0. Now, I would like to remind you what the graph of tangent looks like. It's this squiggly thing. Woo, woo, wee, wee, like a roller coaster, but with trig. And in particular, what are the zeros of tangent? They're the same as the zeros of sine, which is 0, pi, 2 pi, but also minus pi, minus 2 pi. And in case you're wondering if you came to the right channel, you did, because the zeros of tangent are precisely Peyam. Peyam, where m is an integer. So 0, pi, 2 pi, 3 pi, but also negative sign. So in particular, to continue with that problem, we then get minus 2 plus c equals Peyam. So c is 2 plus Peyam. And so what is the general solution, or like what is the solution in this case? Y is tangent of minus 1 over t minus t plus 2 plus myself. But it turns out, weirdly enough, we didn't need any of that because tangent is pi periodic. It's pi periodic. So tangent of blah plus any multiple of pi is just tangent of the original thing. So y is in fact tangent of minus 1 over t minus t plus 2. And I know it's unexpected trick, so surprising trick, but that's not really the point. The point is this is a faster method. And if you watch the previous video, you might say, oh, those look like very different methods, but they're actually the same method. Because note, if you solve this equation, this ODE, using the previous method with the U sub, method, which was more rigorous, but a bit slower, you would have gotten the following. You would have obtained the following: integral of 1 over y squared plus 1 times dy over dt dy. Now, just integrating the two equations equals integral of 1 minus t squared over t squared dt. And then using a u sub, you would have obtained 1 over y squared plus 1 dy equals integral of 1 minus t squared minus 1 dt. Which, if we scroll above, is actually the same equation as before. You see this one, this integral of dy over y squared plus 1 equals integral of 1 over t squared minus 1 dt. Which, what's my point? My point is, it seems like a non-rigorous method, but it's actually rigorous if you use a u sub that we did before.